Okay, so what I want to do today is first of all just recap what we were doing at the end of last time, or in the second half of last time. So we'd introduced the idea of a group, which is the key concept for the rest of this semester that we're going to be exploring, and it'll also come into some of next semester's work as well. So from now on we're focusing on groups, and remember the idea of a group is built on what we were doing in the first few weeks, which was looking at sets with a binary operation. And as I'm going to remind you in a second, a group is just a set with a binary operation where the binary operation has nice properties that enable us to do things that we want to do. We had quite a few examples of groups last time, and what I'm going to do today to start with is just a few basic properties of groups that can be derived easily from the axioms. So in abstract algebra and other parts of maths, as you're probably beginning to realise, even after work in year one, we have this kind of axiomatic method. So we write down some basic axioms or statements that our structure is going to obey, like we've got those three axioms for a group, you had axioms for a vector space, you have axioms for a graph. So whatever theory you're doing, whether it be group theory, linear algebra, graph theory, you have some axioms, and then from those axioms you prove theorems. Sometimes you have to have extra definitions as well. Then you prove theorems just based on the axioms, and because the theorems are just based on the axioms, any system that satisfies the axioms, automatically the theorems that you've proved will hold for that system. So in other words, you don't have to keep reproving things. So for instance, we might be looking at the group of integers under addition modulo 8, and we might be looking at some group of matrices which looks completely different. But if we've proved some statement that applies to all groups, then that statement will apply to both integers modulo 8 under addition and some group of matrices under multiplication. We don't have to prove something for each example separately. So that's the idea of the axiomatic approach. So just a reminder about what a group is. So we defined it properly last time, so I'm just going to do a sketch definition here. Of course, all these definitions are in the lecture notes, which I hope you're all looking at regularly. That's what they're there for. So a group is a set, which we tend to call G now, G for group, equipped with a binary operation. And we have three axioms that this binary operation has to satisfy. Firstly, it's nice to work with associative binary operations. So we'll always assume that our binary operation is associative. Star has an identity element. It's nice to have an identity element, so that's a special element in the set which behaves well with respect to the binary operation in a particular way. And we know from previous work that if a binary operation has an identity element, then it has precisely one. And so we can give this unique identity element a letter. We'll usually call it E generically, although in this particular case it might be called 0 or 1 or the identity matrix. But the generic letter for an identity element will be E. And we also assume that every element of G has an inverse element. In other words, for every element in G, there exists another element of G, which is it kind of undoes G in the sense that if I do G prime and G with the binary operation, I get E, and also the other way around. So I'm using fairly abbreviated notation here. So every element has an inverse. And these three properties give us a lot of power in terms of what groups can do for us. And what we did prove last time, one of the first things we did with our axioms was prove this proposition. Well, G2 about identity elements, we already know that says that if there is one, then it's unique. Well, there's a similar thing for G3, that if we've got a group And I'm going to start being a bit sloppy now in the sense that if I say let G be a group, what I really mean is let G comma star be a group. But as long as we understand the binary operation is there, we don't forget it, but we don't mention it all the time. We often just say let G be a group. That is sloppy because G is really a set, and it's the pair G with its binary operation that's a group. But often we're sloppy and just say let G be a group. But don't forget there's a binary operation locus. And also don't forget that the same set could have lots of different binary operations. So you do need to know what the binary operation is. And let's take an element of G. So I'm using big G here to mean two different things, both a set here and a group here. So the context should make it clear. And the statement is G has exactly one inverse. And we've got, since there's only one, we can give it a special name, and we use index superscript notation. So this is what we did last time. Okay, the inverse of G is denoted G to the minus 1. That's multiplicative notation. If we were using additive notation, the inverse of G noted minus G. But our generic multiplicative notation, we use G to the minus 1. So in other words, G inverse is the unique solution of the equations G inverse star G equals the identity, and G star G inverse is the identity. So those simultaneous equations have precisely one solution, which we call G inverse. We have to write both of those down because we want our inverse to work both on the left and on the right. And if our binary operation is not commutative, then having it on the left might not mean that it works on the right as well. So we want it to work on both sides. It's a two-sided inverse. So that's just a review of what we did last time. So what I want to do first is just some consequences, useful consequences of this proposition. And we use these results all the time. In fact, you already use some of these, if not all of them, in different examples. And I'll write them down and then perhaps just prove one or two of them. So this is a corollary of the proposition, really. That if we take the identity element and ask, well, the identity element is certainly an element of the group, it's a special element. What's the inverse of the identity? Well, the answer is the inverse of the identity is itself. Okay? So when you're multiplying numbers, the inverse of 1 is just 1. When we're doing addition of numbers, the inverse of 0 minus 0 is 0. The inverse of the identity matrix is itself, and so on. That's true in any group. Well, suppose I take an element in the group, then I've got its inverse, but the inverse of G is also an element of the group. So I can ask the question, what's the inverse of G inverse? It's got a unique inverse, and we should be able to answer the question, what is G inverse or inverse? Any suggestions? G, good. What else could it be? The inverse of the inverse is, you get back to where you started. And you're quite used to that. If you're working under multiplication in the rationals, the inverse of 2 is 1 over 2, and the inverse of 1 over 2 is 1 over 1 over 2, which is 2. Okay, so you get back to where you started. And thirdly, suppose you've got two elements of the group. How does the inverse interact with the binary operation? Well, what does that mean? Well, I can multiply G and H together using the binary operation, and then I can say, well, G star H is an element of the group. So I can ask the question, what is the inverse of G star H? Any suggestions? You've seen this for matrices, and we did actually touch on it in one of the tutorials yesterday, I think. Can't remember which one now. But you've seen this for matrices already. What's the inverse of a product? You expect it to be something to do with G inverse and H inverse. You should have seen this for matrices in year 1. Well, it's actually the product of the inverses, but in the other order. It seems that you might have forgotten that, but that's certainly true of matrices. Well, it's also true of numbers. If when you're adding and multiplying numbers, you don't notice a change of order of course, because the binary operation there is commutative. Well, let's prove one or two of these. The proof of all of them are in the notes. Let's prove, say, 2. So let's consider the element G inverse in G. Just thinking of G inverse as an element of G. Well, what does the inverse of G inverse satisfy? So the inverse of G inverse is the unique solution. Let's call it U for a minute, because we don't know what it is yet, of the equations. So U is what we're trying to find. U is the inverse of G inverse. So if I do U with G inverse, I get the identity. And if I do G inverse with U, I get the identity. So that's writing down the inverse simultaneous equations applied to G inverse. So U is going to be the inverse of G inverse. It's the unique solution of these equations. Okay, that's just by definition of the inverse. And we know from the proposition that there's only one of them. But we know that we can spot a solution of these equations straight away. U equals G satisfies these equations. Because if we swap them round, using the symmetry of and, if we swap these round, we just have precisely the definition of the inverse of G. Okay, so U equals G satisfies these. And since there's only one solution, U must be equal to G. So observe that U equals G satisfies these equations. And there's only one solution, so hence we have G inverse must be G, because G is the only thing that satisfies these equations. So the inverse of G inverse is G, and we use that result quite a lot. The inverse of an inverse is the thing that you started off with. Well, I won't prove the other two, but they're similar. What you do is you write down the simultaneous equations for the inverse, and then spot that the only solution is what these results say. So you can do that for 1, for 3. Okay, so I'll let you make sure that you can read through the proofs in the notes. If you have any problems with those proofs, I mean, they are the kind of thing that you could be asked to do. They're only short little proofs. If you have any problems with those, you can ask in the tutorial next week. Okay, so I've just done one of them, but 1 and 3 are similar. So we do use these 3 results quite often. Any questions about that? Is that all okay? So these are very basic group theory properties that we use all the time. And I now want to mention another property that we use all the time, and this is called well, it's usually called the cancellation lemma. So a lemma is kind of a little result that's usually used to prove other things, and we will use this lemma to prove something quite useful in a second. And it basically says that in a group we can cancel on both sides of an equation in the way that you would want to. So it's basically related to that pizza dividing problem we did last time, which motivated the definition of a group. We can cancel on both sides of an equation. Okay, so suppose we've got A, B, and well, perhaps I should say let G be a group, or G star be a group, and let, say, A, B, and C be elements of G. Well, there's a cancellation lemma on the right and there's a cancellation lemma for the left, and we'll write them both down. So if A star B equals A star C, suppose it happens to be the case that A star B is A star C, then we can cancel an A on the left and deduce that B equals C. We want to be able to do manipulations like that, and the group axioms let us do that. So being able to cancel like that is good. And then there's a similar one for the other side. So if B star A equals C star A, so this is where the A is on the right, again B equals C. So we can cancel on the left, or we can cancel on the right. Notice the A that we're cancelling has to be on the same side, either left or right, on both sides of the equation. So let's just do one of these, and the other one will be similar. So we're going to suppose that A star B equals A star C. Oops. And we're just going to use group axioms and what we've proved already about groups to deduce that B equals C. So we want to get rid of the A. How do we get rid of the A? What can we do to both sides of this equation to start the process of getting rid of A? What device do we have to kind of kill off A? Yeah, we're going to use A inverse and get A inverse next to A to get rid of A. So then, well, I'm going to put A inverse on the right, well, the correct side, which will be the left side. So I'm going to do A inverse star A star B equals A inverse star A star C. So what I've done there is taken this element A star B and pre-multiplied it by A inverse, and similarly on the other side. Now, I'm urging you all to get into the habit of writing down right-hand reasons, which I'll expect to see in your work. Well, I haven't got a lot of room here, but I'm saying what the right-hand reasons are, so I urge you to write them down. So this follows from this. You could say multiplying on the left by A inverse, or pre-multiplying by A inverse, or something like that. So that when you come back to read it, or somebody else reads your work, they can see why one line follows from the previous one. You might be glad of those reasons when you read through your own work. Okay, well now what are we going to do? Any suggestions what we're going to do next? We're going to use associativity. In a few weeks' time, when you're a lot more confident with group theory, you'll just be doing some of these lines two at a time, perhaps, jumping two at a time. But I'm trying to write down every single line at the moment until we get a bit more fluent in group theory language. So I'm going to move the brackets using associativity, because our binary operation is associative. So the right-hand reason there is using associativity of star, something like that. because remember we're working in a group, so we do have associativity. Well, the reason we multiplied by A inverse on the left was so that A inverse could get next to A. And when A inverse gets next to A, by definition of A inverse, or using half of the definition to be precise, we get the identity element. So that's property of A inverse or something. It's kind of half of A inverse's power, isn't it? Because A inverse would also work on the other side. So we're using the fact that A inverse is a left inverse there. Everybody happy with that? So we're redoing the pizza problem here, but in a general abstract setting. Now we use the fact that E is an identity element. E star anything is the anything. So we end up with B equals C as we wanted. So the reason for that step, going from this line to this line, is using properties of the identity element E. Okay, so we've deduced that B equals C, which is what we wanted to do. So it's not a super deep theorem, but it's very useful. So as soon as we see AB equals AC, we can just cancel an A on the left and start simplifying our equations. Well, there were two parts to this little lemma. What word could we use here to save ourselves some time? A word beginning with S, and it would be perfectly legitimate to use this word here to save ourselves writing out what would look very much like that, something that would look very much like that. We could use a word beginning with S.
Similarly.
Good, similarly. It's a very useful word, but you've got to use it honestly. So you can see that you've just been post-multiplying or multiplying on the right. So similarly, B star A equals C star A implies B equals C. So you've saved yourself some ink and some time there. Don't put similarly if the proof is going to be completely different, because that would be dishonest, right? But this is clearly going to be a very similar proof. It's just that the A inverse would be on the other side. And you'd be using the other half of the properties of inverses and the identity element. So similarly is a useful word, but use it appropriately. And that's perfectly fine. If that was an exam and you did that, use the word similarly there, that you get full marks. Okay? It's only when this would look different or there's a little twist going the other way that you wouldn't use similarly. But that's kind of mathematical maturity. You'll gradually get a feel for when it's okay to use similarly. Okay? So the cancellation lemma is again a basic result of group theory we use all the time. We can cancel on the left, we can cancel on the right. Which is good. And let's do a little application of that now. Suppose G is a finite group. So when I say G is a finite group, I mean that the underlying set is finite. And we've seen a few examples of finite groups. So if it's not finite, we say it's infinite, and we've seen examples of infinite groups as well. So finite is just referring to the underlying set. You know what a finite set is, you know what an infinite set is, and we can use the same word for groups. By the way, for a set, we tend to use the word cardinality for the number of elements in a finite set, but for a group we tend to call it the order of G. So the number of elements in a group is called the order. That's just historical reasons. For a set you'd say the cardinality, for a group we say the order. But the order of a group is the cardinality of its underlying set. So I'll often talk about the order of a group. Well, for a finite group, we've got a binary operation, and if we've got a binary operation on a finite set, we can draw its multiplication table. Well, we can do the same thing for a group, and we were doing a bit of this in tutorials yesterday, the multiplication table for a group, again for historical reasons, has a special name. It's named after an English mathematician of the 19th century. It's called its Cayley table. So Arthur Cayley was an English mathematician of the 19th century, a very important English mathematician of the mid-19th century, well, early to late 19th century, and he did a lot of work on group theory, and so group multiplication tables are called Cayley tables after him. So an example we did which came up in one of the questions on worksheet 3, if we took G to be these integers modulo 8, and star is addition modulo 8, multiplication modulo 8. So as we explained in the tutorial yesterday and we've mentioned before, these aren't really numbers, they're equivalence classes of integers, which we can multiply modulo 8. So the Cayley table for this, we actually drew in the tutorials. Oops. I'm carried away there. So this is multiplication modulo 8. Sorry, that's a 5. So there are four elements in the group. It's a group of order 4. So there's going to be a 4 by 4 Cayley table, and we actually filled this in. One is the identity element. So we get the top row and the left-hand column for free. I would always fill that in first, and then you just have to compute. And in fact, what we found yesterday was we got 1s all the way down the diagonal, because any element squared is equal to 1. And then we got 3 5s is 7, 3 7s is 5. And it was an abelian group, because multiplication modulo 8 is commutative. So we got that. So we did that in the tutorials yesterday. So that's multiplication modulo 8. So for example, 5 times 7 is 35, but 35 leaves the remainder 3 on division by 8. So 35 is equivalent to 3 modulo 8. So we've got a binary operation on these 4 elements, set of 4 elements. Identity element is 1. This is associative, because multiplication of modulo 8 is associative. And every element has an inverse. In fact, the inverse of every element is equal to itself. So how do I know that? What's the inverse of 3? Well, it's the number I have to multiply 3 by to get 1, which happens to be 3 again. So in this group of order 4, every element is equal to its own inverse, which of course doesn't happen in every group, but it happens